Hello everyone. In this lecture we will discuss about the mass transfer correlation. The mass transfer correlation. In the previous lecture we have discussed about the diffusion through a stagnant layer. So this in the previous lecture we have discussed that there was a spherical catalyst pellet and a fluid was passing around the spherical catalyst pellet. This was a fluid and there was some a boundary layer or form around the this was the hydrodynamic boundary layer. This was the hydrodynamic boundary layer around the spherical catalyst pellet, and the velocity of the fluid was this u, and this was the bulk flow. This was the bulk flow region, and this was also a bulk flow region. Bulk flow region. And we consider that this was the hydrodynamic boundary layer. We consider a thin layer inside the hydrodynamic boundary layer, and we determine the flux through the stagnant layer in the z direction. So this was z, and this was z plus delta z. The thickness of the stagnant layer was delta z. We determined the flux of component A in the z direction through this stagnant layer, and the flux through this stagnant layer was WAZ is equal to the diffusivity of component A and B divided by thickness, the concentration of component A at the surface of catalyst minus concentration of A in the bulk. So this was bulk flow. This was bulk flow. The concentration of A in the bulk flow was CAB, and the concentration of component A on the surface of catalyst was CAS, and this was the thickness of the hydrodynamic boundary layer. The thickness of this hydrodynamic boundary layer was sigma. So now this, and we obtained the flux through stagnant layer which was present around the catalyst pellet. Now this was the thickness of the boundary layer. Now we can further write this equation, this flux, in this way: WAZ is equal to Kc CAS, concentration at the surface of catalyst, minus concentration in the bulk flow. Now what is this Kc? This Kc is called the mass transfer coefficient, and the mass transfer coefficient is nothing but diffusivity divided by thickness of the hydrodynamic boundary layer. So the DAB divided by thickness of the hydrodynamic boundary layer is equal to the mass transfer coefficient. This is the mass transfer coefficient. In the heat transfer, a similar relation can be obtained using the Newton law of cooling. So the heat flux in the z direction will be equal to the heat transfer coefficient into the temperature gradient. So T1 minus T2. So this is the heat transfer coefficient. Now there is a correlation for the heat transfer. Suppose if a spherical particle, suppose this is a spherical particle, and there is some fluid is flowing around the spherical particle. So and suppose this is a fluid flowing around the spherical particle, then the heat will transfer. Either the heat will transfer from the flow toward the spherical particle, or the heat can transfer from the spherical particle to the cold fluid. So if this fluid is cold, then heat will transfer from pellet or spherical particle to the fluid, or if the fluid is at very high temperature, then heat will transfer from the fluid to the pellet. Now then how will we determine the heat transfer coefficient in that case? Suppose this is a fluid flowing around the spherical particle. This is a spherical particle. Then how will we determine the heat transfer coefficient in that case? So the heat transfer coefficient in that case will be determined by using a correlation, which is Nusselt number is equal to 2 plus 0.6 into Reynold number to the power 1 divided by 2 into Frontal number to the power 1 divided by 3. I am coming to the mass transfer, but first of all you should know about the heat transfer correlation. So once you know the heat transfer correlation, you will easily determine, you will easily understand the mass transfer correlation also. So this is for the heat transfer. Now once you determine the Nusselt number, you will determine the heat transfer coefficient, which is this H. So, and which is present in the Newton law of cooling, which is Q is equal to H, the heat flux in Z direction, and T1 minus T2. The T1 can be this, T1, T2 will be suppose on the surface of the pellet T2, so you can determine it. Now what is this, these number, these number, these are the dimensionless number. This is the Reynold number, Re is the Reynold number, and PR is the Frontal number. Reynold number is equal to the rho V into diameter of the particle, density of the fluid, velocity of the fluid which are flowing. The velocity of the fluid is V, the diameter of the fillet is D, P, and the density of the fluid is rho, and the viscosity of the fluid is mu. So the viscosity of the fluid is mu, viscosity of the fluid. Now once you know these terms, you will determine the Reynold number. Now put the Reynold number in this equation, you will get the Nusselt number, but you should also know the Frontal number. So what is Frontal number? It is also a dimensionless number, and it is a ratio of momentum diffusivity divided by thermal diffusivity. Momentum diffusivity is equal to, the momentum diffusivity is nothing but viscosity of the fluid divided by density of the fluid. So viscosity of the fluid divided by density of the fluid. What is thermal diffusivity? Thermal diffusivity is nothing but it is the thermal conductivity divided by density of the fluid into the specific heat of the fluid. So K divided by rho Cp, K divided by rho Cp, cancel with this. So Cp into mu divided by thermal conductivity is nothing but the Frontal number, Frontal number. So if you know these term, you will determine the Frontal number. Now put Frontal number, Reynold number in this correlation, you will determine the Nusselt number. Now once you determine the Nusselt number, suppose the Nusselt number come out to be 5, then how you will determine the this heat transfer coefficient? So this heat transfer coefficient is related to the Nusselt number by a relation. Nusselt number is equal to the heat transfer coefficient into the diameter of the particle divided by thermal conductivity of the material. So if this is come out to be 5, so suppose this is 5. If the thermal conductivity will be given to us, suppose thermal conductivity is 1 and diameter of the particle suppose 1 centimeter. So the heat transfer coefficient in that case will be 5, and the unit, you will be write the unit of heat transfer coefficient, the heat transfer coefficient unit. You can determine the heat transfer coefficient, unit of heat transfer coefficient by using this relation, the temperature gradient. So this is the heat rate, so this is watt per Kelvin is the unit of the heat transfer coefficient, or joule per unit time into Kelvin, you can write the unit. Now for the mass transfer, now suppose there is a spherical catalyst particle which are present in a large stagnant liquid, is a large stagnant fluid, and suppose there is a spherical catalyst particle which are present in this large stagnant liquid, this is a large stagnant liquid. The velocity of the fluid is 0 because the fluid is not moving and it is a stagnant fluid. and a catalyst particle is present, a spherical particle or a spherical catalyst pellet is present, and heat is transferring from, suppose, from the catalyst particle, heat is transferring from the catalyst particle to the stagnant fluid, So in that case, how will you determine this heat transfer coefficient? So in that case, you will determine the heat transfer coefficient by using the above correlation, which is Nusselt number is equal to 2 plus 0.6 Reynold number to the power 1 divided by 2 into Frontal number 1 divided by 3. So Reynold number is density, velocity, diameter of the particle, viscosity. So velocity of the fluid is 0. So this V is 0. So V is 0. So if V is 0, Reynold number will be 0. So when Reynold number is 0, this whole term will be 0. In that case, the Nusselt number will be equal to 2. Nusselt number will be equal to 2. So once you determine the Nusselt number, you will determine the heat transfer coefficient by using the relation, this relation, and this is equal to Nusselt number. So you will determine the heat transfer coefficient. So now if a fluid is flowing around, the spherical catalyst particle, and if the velocity of the fluid is very high, then in that case this 2 will be 0, and in that case the Nusselt number will be equal to 0.6 Reynold number into Frontal number 1 divided by 2, 1 divided by 3. So in that case, Nusselt number will be this, and you will determine the heat transfer coefficient from this correlation and this Nusselt number. Similarly, for the mass transfer, you suppose if this is a catalyst particle, and if there is a fluid which are flowing around the catalyst particle, and suppose if mass is transferring from the catalyst particle to the fluid, suppose component A is transferring from the catalyst particle to the flowing fluid, then how the velocity of the fluid is V, suppose, and this is the velocity of the fluid, then how will you determine the mass transfer coefficient? So in that case, we will use another correlation which is similar to the heat transfer correlation. So the heat transfer correlation in the above case was 2 plus 0.6 into Reynold number 1 divided by 2 into Frontal number 1 divided by 3. This was for the heat transfer. But for mass transfer, we will use similar correlation, but in this number, in place of this number, we will use another number which is Sherwood number, and it will be equal to 2 plus 0.6 into Reynold number 1 divided by 2 and to Schmidt number 1 divided by 3. Remember, Reynold number is same in both cases because fluid is flowing around the catalyst particle. So if fluid is flowing around the catalyst particle, in some cases heat will transferring to the catalyst particle, or heat will transferring from catalyst particle. In some cases mass will transferring from catalyst, in some cases mass will be transferring from fluid to the catalyst. So you will use, in case of mass transfer, you will use this correlation, but in case of heat transfer, you will use this correlation, this above correlation, this black one for heat transfer. This is for the heat transfer, and this one is for the mass transfer. Now what is this SC? This SC is the Schmidt number. This SC shows the Schmidt number, and the Schmidt number is nothing but the momentum diffusivity divided by the mass diffusivity. So the momentum diffusivity is nothing but viscosity of the fluid divided by density of the fluid, and DAB, the mass diffusivity. So this is the Schmidt number. Now what is this Reynold number is same, rho UD by viscosity. And what is this Sherwood number? This Sherwood number is nothing but it is just like the Nusselt number. Nusselt number was equal to H, the heat transfer coefficient, diameter of the particle divided by thermal conductivity of the material. But Sherwood number, in place of heat transfer coefficient, we will use the mass transfer coefficient. And we have already discussed the mass transfer coefficient. How can we obtain the mass transfer coefficient? It was obtained from DAB divided by thickness. So this was mass transfer coefficient. So this is the mass transfer coefficient and diameter of the particle divided by mass diffusive DAB. So once you determine the Sherwood number, you will determine the mass transfer coefficient. So suppose this is a catalyst particle. This is a catalyst particle. This is a fluid flowing around the catalyst particle, and suppose mass is transferring from the catalyst particle to the fluid. Velocity of the fluid is V. So and the diameter of the catalyst particle is dP. The viscosity of the fluid is mu. Density of the fluid is rho. So in that case, what will be the Nusselt? What will be the mass transfer coefficient? So this is a spherical catalyst particle. Fluid is flowing around the spherical particle. In that case, the Sherwood number will be equal to 2 plus 0.6 Reynold number 1 divided by 2 and to the Schmidt number 1 divided by 3. So once you determine this number you will put in this correlation, you will determine the Sherwood number, and the Sherwood number is nothing but the mass transfer coefficient and diameter of the particle divided by DAB. So from this you will get the mass transfer coefficient. So now suppose if a fluid, this is catalyst particle and it is present in a large stagnant liquid, large stagnant fluid. This is stagnant fluid, and mass is transferring from the catalyst particle to the stagnant fluid. Velocity of the fluid is u is equal to 0 or v is equal to 0. So in that case, the Reynold number will be 0, because Reynold number velocity is present. You know, rho v d. This velocity is 0. Velocity of the fluid is 0, because fluid is not moving, so Reynold number will be 0, and this whole term will be 0. In that case, Sherwood number will be equal to 2. Now once you determine the Sherwood number, so the Sherwood number is 2. If this will be given to us, multiply this with this number, and the diameter of the particle, suppose it is 1, so divide it by 2 divisivity of the part of A and B, and diameter of the particle, suppose 1, so you will get the mass transfer coefficient. So put the mass transfer coefficient in the flux. Mass transfer coefficient, suppose this is the value of this one is 3. After simplification, suppose this is 3 divisivity is 3, then that will be 6. This will be 6. So 6 and this is the concentration gradient, CAS minus CAD. So you will get the flux. Now if a fluid is, suppose a catalyst particle, and a fluid is passing through the catalyst particle, and if the velocity of the fluid is very large, then in that case the Sherwood number will be equal to 2 plus 0.6 Reynold number divided by to the power 1 and Schmidt number to the power 1 divided by 3. So if the velocity of the fluid is very large, then this number will be very high. As compared to this this number. So we will get a relation which will be, this will be negligible. So we will get it as 0, and Reynold number 1 divided by 2 and Schmidt number 1 divided by 3. So once you determine the Sherwood number, suppose Sherwood number is 10, then Sherwood number is nothing but Kc and diameter of the particle and to the DAB. So the DAB is given to us, the diameter of the particle usually given to us, suppose it is 1 centimeter, and suppose diffusivity is 2, and suppose Sherwood number come out 10, so this is 10 and this is 2, 10 multiplied by 2, 20 divided by 1, so Kc will be equal to 20. put this one in the mass transfer, you will get the 20 into the concentration gradient. So you will be get flux. So this was just introduction to the mass transfer correlation. I am showing some also mass transfer correlation. These are the mass transfer correlation. There are some these are the mass transfer correlation. You can check it. These are the mass transfer correlation. So these are the mass transfer correlation. These are the mass transfer correlation. If a flow is turbulent, mass transfer to the 5 wall, suppose is a 5 and fluid is flowing and some mass is transferring to the surface of the wall, then and if a flow is turbulent, if Reynold number is very large, it is greater than 4100, so in that case the Sherwood number will be equal to 0.332 Reynold and Schmidt number. So a mass is transferred to a single sphere, then this correlation will be used. We have already discussed this one. Mass transfer in a fluidized bed. So this is a fluidized bed. This is a fluidized, suppose this is a bed, and there is some catalyst particle present in it, and if the velocity of the fluid here is very large, then it will form the fluidized bed. Then this correlation will be used as the J factor, Colburn J factor, and this term shows the white fraction. So this is the white fraction. So usually it is 20% or 30%. Usually it is given to us 20 or 30%. Similarly, this is also a correlation for mass transfer to peg bed. So a peg bed is used, then you can use this correlation. This is the Sherwood number, Reynold, Schmidt number, and this is the J factor, Colburn J factor. So thank you very much for your attention. Thank you very much.